this video, I want to define a permutation. Permutations of a set A are bijective functions from A to A. Another way to think of permutations is a rearrangement of the elements of a set. As an example, let's consider a set 1, 2, 3, 4, 5. Then if we start with them in this order, an example of a permutation would change this 1, 2, 3, 4, 5 to something like 3, 2, 1, 5, 4. So we rearranged the order of the elements. Let's consider this example a little bit more. So like I said, this does need to be a bijective function, so we should take the elements in our set, 1, 2, 3, 4, 5. 1 is going to map to 3 since I changed the first spot from a 1 to a 3. The number 2 changed to a number 2, so 2 maps to 2. The third spot changed to a 1, so 3 goes to 1. The number 4 changed to a 5, so 4 would go to 5. And then finally 5 turned into a 4, so the 5 would map to 4. So this would be my bijective function. Let's consider some things we know about these bijective functions. The first thing, the composite of a bijective function is a bijective function. So combining two bijective functions under composition still gives me a bijective function. And this is something I proved in another video. To relate that back to my permutations, the composite of any two permutations of A is another permutation of A, since these permutations are just bijective functions. This then gives us that the operation of composition is an operation on the set of permutations of A. So I have defined an operation on my group of permutations. While I will not prove it directly, composition is associative, so my associative property does hold for this operation. In order to show this is actually a group, the next thing I would need is the identity. I'm going to denote the identity function by this epsilon. And the identity is going to be epsilon of x is equal to x. We just take an element and map it to itself. This actually tells us that f of epsilon is equal to f, and epsilon of f is equal to f, since epsilon doesn't actually change anything about this function. Now that I have an identity, I need an inverse. The inverse of a bijective function must exist and is bijective. This is also something I proved in a previous video. This then extends to the fact that the inverse of a permutation of A is another permutation of A. So, not only do my permutations have an identity and inverses, they're also associative, therefore I have a group. We call this the symmetric group, the group of all permutations on A, and it's denoted by S sub A. So S stands for symmetric, and then A for the particular set that we're considering. And if we want to consider the symmetric set on a group of numbers, such as 1, 2, 3, etc., all the way up to n, then we would call that S sub n. Let's look at some examples of these symmetric groups. Let's consider S3, so the symmetric group on 3 elements. The identity, so we write 1, 2, 3 in the first row. The identity would just map them to 1, 2, and 3. Let's call the next one alpha. We have 1, 2, 3. And we're just going to flip the 3 and the 2 to make 1, 3, 2. For beta, once again, I'm going to start with 1, 2, 3. And this time, I'm going to map 3, 1, and 2. So the first row is just 1, 2, 3. The second row tells me what I'm mapping each of those elements to. Gamma maps 1, 2, 3 to 2, 1, 3. Delta maps 1, 2, 3 to 2, 3, 1. And finally, kappa will map 1, 2, 3 to 3, 2, 1. So this is all of the ways to rearrange 3 elements. Let's look at giving a group table. So we would have epsilon, alpha, beta, gamma, scroll down just a little bit, delta, and kappa. Across the top, the same thing. And then we want to build this group table out. Since epsilon is the identity, it doesn't change anything, so everything stays where it is. And now I want to do the rest. And we have to remember that we're doing composition. So first, alpha composed with epsilon. Well, anything composed with epsilon is going to be itself, since that's the identity element. And then alpha composed with alpha. So we have to consider this twice. One maps to 1, and then 1 maps to 1. So 1 will map to 1. 2 maps to 3, and then 3 maps to 2. So that tells me that 2 went to 2. Then finally, 3 went to 2, and 2 went to 3. So I'm back at my identity element. Next, we have alpha composed with beta. And so we have to remember that we're talking about composition, so we have to do beta first and then alpha, since composition works from the inside out. So 1 maps to 3 and 3 maps to 2, so 1 would map to 2. 2 maps to 1 and 1 maps to 1, so 2 maps to 1. Here we have 3 mapping to 2 and 2 mapping to 3, so 3 maps to 3. And we can see that this is equivalent to delta, or gamma. Next, we have alpha composed with gamma. Once again, start with gamma and then move to alpha since it's composition. 1 maps to 2 and 2 maps to 3, so 1 maps to 3. 2 maps to 1 and 1 maps to 1, so 2 maps to 1. 3 maps to 3 and 3 maps to 2, so 3 maps to 2. And this would give me beta. The next one we want to do is alpha composed with delta. So we start with delta. 1 maps to 2 and then 2 maps to 3, so 1 goes to 3. 2 maps to 3 and 3 maps to 2, so 2 maps to 2. 3 maps to 1 and 1 maps to 1, so 3 maps to 1. And we can see this is equivalent to kappa. For the end of this row, we have alpha composed with kappa, so we need to start with kappa. 1 maps to 3 and 3 maps to 2, so 1 maps to 2. 2 maps to 2 and 2 maps to 3, so 2 maps to 3. And 3 maps to 1 and 1 maps to 1, so 3 goes to 1. And this would be the same as delta. And we can continue this process. While I will not work through this whole table, I highly encourage you to go ahead and try some more of these. If you work out the table, this is the rest of what you should get.